Hi everyone, good day. I cannot say good morning, but it's good day. Right? I would like to mention to thank my co-authors, my student Van Nguyen, and Stelios and William, are collaborators from Washington State. Most of the what I present here, some has not been published, but most of them are joint work with them. So. So I will start with some motivation and then define the problem and then look at that in the under the logic programming framework and then have like discuss its applications, the related work, and then so in the last few years, so our interest in the topic explainable AI really start from the time when DARPA has a program call for proposal on XAI, in which it was discussed. And when they mentioned the AI system here, they mostly mentioned mostly thinking about the machine learning system. At that time, as you all aware, that AI system like face recognition, learning, like it applied in many applications, and they try to apply that in many applications like transportation, security, medicine, and so on and so forth. But then something happened, and it probably the same as in Europe, where slowly it starts the law of knowing. So the law of explanation, right? The user have to be able to get the explanation about why the system is doing this and why not that, and so on and so forth. There are a lot of questions that was raised in this proposal, and they proposed the three themes, like first, producing explainable models. Because of the machine learning system are inherently unexplainable. So that's one of the goals that they do. Designing explanation interface, understanding psychological requirement for effective explanation. So that basically boiled out to three areas, like computing the answers, designing the human-computer interaction, and psychology. Now, our interest steer from this, but it actually inspired by the explainable planning community. What they do, they come up with the following context of human and robot working together, and then the human ask the robot to accomplish a task, and ask how the robot would complete it. The robot present a plan, and the human looking at the plan may have a different plan that he thinks is better than the proposed plan, and so it asks for explanation, right? And so what they introduce the problem called model reconciliation problem in explainable planning. In this case, so at that time, the assumption was the robot knows both models. So it knows the model MH of the human, but it also have its own model. So it try to search through all possible connection somehow. We will talk about that later, like create a different model from each own, but not deviated from its own model very much, but then can explain to the human basically what the models of what is missing or redundant in the human models that prevent the human to see that the plan it is presented is the optimal plan. So, and the goal in this problem in explainable planning was how to compute this explanation, right? So what I wanted to present in this talk is the we take that inspiration, we investigate the model reconciliation problem under the lens of logic in a more general term, and I wanted to show that the generalization of this problem can be effectively used in explainable planning, and as you can see, and in more other applications. In that, in this work, we appeal to the notion of an explanation. It's a set of statements usually constructed to describe a set of facts, which clarifies the causes, the context, and the consequence of those facts. This description may establish rules or law and may clarify this. So basically, this is an explanation from the logical perspective. It was given like just like in this book. As you know, that I think that in the other workshop there are discussion about like the theory of explanation and all these things. At least in this talk, in the work that we do not like, we just focusing on the explanation as such. And now I would like to introduce you to the model reconciliation problem in general term that we developed. From the representation perspective, we view the robots and the human, each of them have a knowledge base. So a logical theory KBA and KBH in some logic L respectively. So the knowledge base does not necessarily represent the true fact of the world, but it could be the belief of the reasoner and so on and so forth. And so we assume that the logic L will come with the notion of models, the entailment, and these two relationships. We have the credulous entailment, like denoted with the superscript C here, and the skeptical entailment noted with the superscript S here. Okay? And the exchange between the two, between the human and the robot, are basically question about the truth value of formulas over literals occurring in this logical theory. And what would be the answer? What would be the answer? So the explanation here is the suggested modification to the knowledge base of the questioner. And more precisely, we consider two types of questions that we think would be sufficient to represent all kinds of questions. One is entailment model reconciliation, and that is from the perspective of the agent. So human asks, why is the formula 5 not skeptical entail in my theory, but in your theory? And the non-entailment reconciliation problem is why it is happening on why it is entailed in my knowledge base, but not skeptical on your side. Okay? And what would be the solution that or an explanation in this case? Right? In the first case, so in both cases, we try to determine a subset of the knowledge base of the agent, epsilon plus, and the subset of the knowledge base of the human, epsilon minus, and update the human knowledge base by taking away the epsilon minus and added the epsilon plus, so that it gives the same entailment relationship between the updated knowledge base and the query. Right? And we call that as the solution of the problem. The term, or an explanation here, the solution is the term that was used by the MRP community in the explainable planning. So we keep it as a solution. Now, the interesting part is like, how do we compute this solution, right? But before we're doing that, it is obvious for us to see that here, for example, if we have a problem stated by a KBA and KBH and a formula, and KBA always satisfies that formula in either case, right? So the simplest case and the most trivial case that the robot just keeps the knowledge base of its own to the human, and so and then it will work. So that basically, but that's not the thing that we really wanted to do. Like here, for example, here we have Wi-Fi is an optimal plan and Wi-Fi not an optimal plan. So the robot doesn't want to basically just tell the human that this my problem is like this, your problem is wrong. So it could be, so we come up with a few characterization of the solution first. Like here, for example, we have, if we have a problem represented by the triple and a solution epsilon plus and epsilon minus, we say that it is optimal if there is no solution, and that is like the union of the two components is a proper subset of the union of epsilon and epsilon minus. So, and this is what most of the time that people are interested in, but there are cases where we really wanted to keep to restrict the explanation to certain subset of the agent knowledge base. So we require that epsilon plus is subset of a knowledge base of pi, which is a subset of KBA. And we say that it is minimally restrictive if there is no solution, no other solution lambda plus lambda minus, such that lambda plus it. So in here, the thing that we concern most about is the adding to the knowledge base than the deletion. But the converse of that is we consider the pi preserving, where pi is a subset of KBH, and pi need to be intersection with epsilon. So I don't want to remove anything from this pi in the KBH, right? And we say that it is maximal preserving if there is no solution, other solution, such that so in here, how much information you added to the human knowledge base, I don't really worry about, but I want to take care of this the deletion from the knowledge base. And some quick notion, like here, for example, with optimal solution is because of the trivial solution always exists, so optimal solution is always exists. Right? But pi restrictive is like existential. It exists and depend on this predefined pi. And minimal restrictive, this also exists, and so on and so forth. So whenever we restrict to this pi, we will see some of the problem, some of the example next here. But so the other characterization of the solution can be done by a cost function, and this is used more often than the other characterization. Basically, we assume that there is a cost function from formula in KBA and KBH to a non-negative number, and define easily. We can define this cost function here. The cost of the solution is basically the sum of the cost of each of that. We say that it is cost optimal if it is minimal among all the solutions. And some special cases, like when we have the cost is uniform here, like when the cost for everything is the same, positive. If it is agent bias, we have the cost of adding rule or adding formula from KBA, it's like, but 0 for removing, and vice versa, human bias. And the relationship between this cost optimal solution and we respect a uniform function. So if it is cost optimal solution, then it is optimized in the ascent of the subset, but not always vice versa, right? So that cost optimal solution, it here it like see if it is agent bias, then it is minimally restrictive, and it is so the relationship between the characterization and the other characterization is in there. Now, as I mentioned, the interesting part in like the explainable planning community's interest in computing this solution, and we can easily have a generate and test algorithm look like this, right? So here, basically, we wanted to have a solution. We can just randomly, like non-deterministically select a potential explanation, a solution, and then test it and return it, right? But here it is assumed that we have like we have two procedures that verifying the entailment, like verifying the credulous entailment and verifying the skeptical entailment. I should note that this procedure is general like this, but we can basically refine it so that we can get to the optimal solution in a faster way. And this is what like using and specifically if we use SAT or unsat, a lot of techniques could be applied to do that. And Stelios, Stelios, William, and their collaborator managed to show to use a heating set to prune the search space and have a system that it's in the last TPI. So they develop a system that is quite good, and it I believe it is better than the other approaches to that date, right? So now I discussed the model reconciliation problem in a very general term there. And now I wanted to focusing on the problem in logic programming. So this is one slide for logic programming, just in case. And I think that the audience, many of you know logic programming, but some of the notion here I wanted to highlight a little bit here. So we consider logic program a set of rule of the form A0 is the head of the rule, and then this is the positive part of the rule, and the negative part of the rule. That with this notation like H of R, positive or negative, right? So the note here is negation operator. The semantic of we consider the logic. So the semantic, the answer set semantic here, and if we have a set of atom S, pi to the S denotes the Calhoun-Lipschitz reduction of pi with respect to S. T pi is the immediate consequence operator for positive program. And then we say that S is an answer set of the program if it satisfies this equation. It is a least fixed point of the TP operator applying on pi to the S. And then here we have like the credulous entailment is pi to the A if A is in some answer set, and pi not the case, not to A is not in answer set. So and then we say that a set of rules is a justification for Q with respect to an answer set I if this condition is satisfied. Basically, the justification not only tell me that this atom is in answer set, but it also give me a proof for that answer set. That is what we're going to use. The problem is formalized in logic programming. It's exactly the same as before. It's just the difference is that now the knowledge base are instantiated by the logic program, and we make it like we consider the general cases where this phi is two conjunction, one a plus and another minus. The reason is the following. So the question that was arise could be like, why is it's a combination of entailment and non-entailment. So if phi is the conjunction two parts, the phi plus and phi minus, so the question asks, why does the agent program entail phi plus and does not entail phi minus? And this is happening, for example. And the solution is defined exactly the same, taking away some part of the program by H and adding some rule from the program by A, so that the condition, this condition like entailment for phi plus and not entailment from phi minus exactly the same. So basically, pi A and pi A have the same answer with respect to phi, right? So that's the idea. And so in explainable planning here again, we have like if pi A and pi H represent the planning problem of the two like of the agent and the human, using the conventional answer set planning and coding with the goal n to indicate that the goal of the problem is satisfied by at the time n, at the step n, and then here we have like so this is the phi plus part, and then this is the phi minus part here. Like why is the goal not satisfied in any step before n, and then and it's satisfying? So that is the goal, right? So just to give you some example here, like a concrete example. So if I have the agent program consists of A and B imply A, B if A, and the human program is just the fact A, and here we have the question is just containing the positive part. So human asks why my program does not entail B. Then the solution here is that, well, you're missing this rule, right? Another program, like in here, this program, it has two answer set, A or B, right? And then here, the human have just the A, and the question is the same, like why I might. So here, the solution is more complicated, and we have to remove the fact from the program, from the human program, right? To get it. Otherwise, we don't have this one. And sometimes the solution could be sometimes the removing of rules could be to restore consistency, as in this example. So in this program, the agent program also still entail B, but the human program is inconsistent, and so that it's like so we have to add this rule and then remove this rule. So this rule must be removed, because even added to that will not make the program consistent. Therefore, we have to remove it. So now, as I mentioned earlier, we could use the general algorithm that generate and test algorithm to generate a solution, but that in the wake of like the multiple like exponential possible potential explanation that would be not scale up. And so we have we use how we generate a new idea of how can we solve the problem. Sorry. And the idea is that, well, if we wanted to make Q true in the new program, in the update program of the human, then the easiest way is to basically create, like, add a justification for Q with respect to certain answer set that supporting Q, right? So that one. And then the E minus is, we need to basically remove all the rules from this human program that prevent the application of the rule in this E plus. Like, so that is exactly what we do here. So I will not going into details of this theorem, but basically what we come up with is like a way to remove rule from a program that prevent a set of rule that is going to be added. So basically, this residual of the program with respect to a given set and an answer set here. So we just so I don't want to go to, basically we just need to remove rule that the idea is to prevent the whole program, to prevent the rule in E plus here. It's the applicable, and we show that this is basically, if we do so, then the program is a solution for this positive, so the Q here. Okay? And we implemented it. Basically, we can implement it using basic like a trick, like if we wanted to solve this general problem, we create a new program by A and I. So we find an answer set that's supporting the W plus, and basically we make sure that everything in the positive question in the W plus have to be true, and then we try to identify the rules that are applicable in the answer set I, and edit a kind of a flag, tagging it with the notion OK X here, and then minimize the set of rules that we need to pick up. So after we calculate this, the answer set of this new program, right? We can get, basically we can get a solution. Now, I wanted to take it a little bit further down to a class of new problem here. So in general, this is what we can do. That is, this is what we can use to solve. But in many in many cases, when pi A and pi H, so when the agent and the human talking with each other, they have a big they basically try to solve a same problem, a class that belong to the same class of problem. And what they do is basically, as you all aware of, like the general methodology of answer set programming is that when we have a problem P, we convert it to an answer set program, and then we calculate the answer set using the solver. And then the thing is that we need to make sure that there is a one-to-one correspondence here. But if we look further down to the details, actually when we did it, the general methodology like can be done applying to any arbitrary program, and anytime you have an instance of the problem, you kind of like do that. But if we wanted to solve a class of problems, what we usually do is that we represent the problem as a set of facts, and I call that FA. And then we develop domain independence rules that when we have the set of facts, it would be instantiated and accordingly. And so we have like basically the program, the final program that we submit to the server change significantly because of the facts, but the set of rules that used to generate them is so in more detail. For example, in planning, the planning problem that consists of the initial state, the goal, and the action effects and the action precondition. They can be encoded as a fact, and this is known. Like, say, for example, we can use the translator that is available from the from the Potsdam group to generate this fact from a PDDL program, a PDDL domain, for example. Then we develop like a very fixed set of rules that like calculate or that for reasoning about action and effect of action and the executability of action and so on and so forth. So this set of rules, basically, this set of rules. So in general, so when we have this situation, the set of rule and the set of the domain independent rule does not change between the agent and the human. The only thing that change is the initial set of facts, right? So therefore, the model reconciliation problem only need to be done at the level of the specification. What does it mean is that, so what is missing or written in the specification, in the problem specification here, the set of facts, that is the thing that it makes a difference. So, and we exploit this idea and basically develop special algorithm for answers for explainable planning that use that idea, and it was presented at KR 2020 that it basically using this idea we can have a lot of like scalability and efficiency there, like so. And the same thing you can do with like scheduling or with all kind of other things. So basically, with this methodology, we can easily generalize the model reconciliation problem for different classes and develop develop like specific algorithm to solve different problems. And explainable planning is one of the examples of that. So now let me spend a few minutes on discussing the related work and the discussion on what go ahead, what lie ahead. So what we can observe is that many problems that was investigated by logic programming community earlier, such as logic program update, or diagnosis or explanation in adaptive logic program. All of them could be viewed as instances of the model reconciliation problem, and specifically model reconciliation problem in logic program. The differences, for at least from my view, is that the differences is that earlier problem, the agent who solved the problem trying to find the self-explanation. Now, in the context of model reconciliation problem, the explanation is to another entity. And so, a quick idea on here, for example, let's look at the logic programming update. We have a program P, we have a new piece of information 5, and we need to update 5 with P. And so creating the update program by 5, here denoted with this. Right? So the general consensus is that 5 must be true in the updated program. And the goal has always been to try to maintaining as much information from P as possible. Now, and the focus in logic programming update is to create to construct this updated program. And there's a lot, a huge amount of literature in this regard, and I will note that. But among them, like there are the causal rejection principle, the program transformation, the two of these two main approaches emphasize the resolution of the conflict that may be caused by including sign to P. Right? So and methods have been updated, developed to help update that obeys it, have to obey the belief revision principle, and so in logic programming update, the specific instance, like the requirement that the rule do not change is not applied. So individual rule could be changes, and here whereas so in model reconciliation problem that it only only adding or removing rules, right? And what is interesting, or what is the surprise, is that the update model may be inconsistent, or the update model may be a set of programs, not just a single program. And we have like so the method that we develop could be applied to computing logic programming update, like by considering this is the agent model. It's just a simple new formula. This is a program of H, and then what it is. But this is not like the one-to-one mapping. It just only work in certain situations. And explanation in abductive logic program, like we have here, and this thing it discussed by Chiaki and Kasumi a lot in the early, like in late 90s. It is this is probably the most similar idea in logic programming that I could find, that is quite similar to model reconciliation. And so here we have a program P and the abducible program A and a query Q. The goal of explanation in abductive logic program is to identify the pair of hypotheses E and F, such that this condition is satisfied. And you can see that it's very, so first of all, they do impose a consistency requirement, and then they also like restrict the what could be added. So basically adding to P and removing. So it's very similar to what we have here now, and that could be viewed as like the program that we have here. So A and P and Q. So that is one of the instances of it. And I should note that Chiaki and Kasumi also introduced the non-entailment query as well. That is quite similar to what we do. Then diagnosis. I should have said. So in diagnosis, we can also have like a set of a theory KB, and a set of observation, a set of predefined atom C, such that I should have here the negation. I'm missing the negation here. That KB union, given the knowledge based observation and assuming that everything is intact, it is inconsistent, and the goal is to identifying a subset of the component, so that, so here it's the negation, so that this is the theory become consistent. And this could be also viewed as an instance of the model reconciliation in logic programming with this triple, right? And I think that I am done with that here. I can make a quick conclusion to show that we formalize model reconciliation form in a very general term, and discuss the different characterization of solution of the problem. And then we investigate the problem in logic programming and the proposed method for computing the solution of the solution in using ASP, and how do we explain, how do we apply that in explainable planning. What I think that it more interested is in the future work. So in the model reconciliation problem, as of like maybe a few months back, I checked, people still assume that the agent who try to explain the problem to the human know the human knowledge base, and that is a very big assumption. This assumption, I do believe it is not realistic, and therefore, in order to address that, one of the way to do that is like the interaction between the agent and the human have to be moving along a dialogue, for example, and then that will be much more interesting. And then the second issue is that here we assume at least the robot or the agent has the knowledge base, has a correct knowledge base. What happens if he doesn't have the correct knowledge base? And that is also very easy to see that this could happen. And so this is the two things I think that is a much more interesting thing that lie ahead of this research direction. I stop here and take some questions.